So my name's Andrew Kirker. It's nice to be in the mainland presenting to you today. I'm the Managing Director of CDC Data Centres for New Zealand, and I also look after our hyperscale business for Australia and New Zealand as well. So I get across quite a bit of the technology and the like. So I'm going to talk to you today about the impact of AI on technologies and eResearch and data centre design. So we'll start by way of an agenda, having a little bit of a look at the good and the not so good around AI, with a few good little examples of what it is that AI thinks about itself. So I'm lucky enough to have the paid version of the Microsoft Copilot. So I've asked it a little bit about what it thinks about itself. And then we'll take a couple of looks at some real-world examples of how this is all playing out. Then we'll take a bit of a look at where IT currently sits and with who. So of all the IT in the world and all the compute, where is it currently sitting and where is it likely to sit in the next generation of compute? We'll take a very, very high-level look at building a large language model, and I'm definitely not the technologist, I'm the data centre guy, so I've massively simplified this down, and I know I'm in a very informed audience here, so we'll take a bit of a look at that, and then we'll take a look at the chips and their evolution, so the workhorse that sits underneath AI, and then we'll drop down into the physical data centre and take a look at what is the impact on that. And then I'll finish with a few little examples of what we've been doing in terms of particularly the area of liquid cooling, which is where the data centre industry is very much heading now. So if we take a look at what does Copilot think of itself, and I simply said to it, what is the advantages and disadvantages of AI? And it basically comes up with lots of different things, obviously, but a very nice, concise little summary. Talks about improved efficiency, particularly in the area of robotics. And I was lucky enough to attend the NVIDIA conference, the GTC, last year in San Jose, and I was just astounded at the progress that robots are making, particularly with the infusion of AI into them. In fact, the best cup of coffee I had the whole time I was up there was from a robot that was infused with the AI of a San Francisco barista. The rest of the coffee was bloody awful. Data analysis and informed decisions, obviously massive data sets. The AI can get through it a lot faster and maybe find things that that people don't detect. Huge advances in medical diagnosis, right? And I met a radiologist on the ferry in Auckland last week, and he'd just retired and he'd been in the radiology field for the last sort of 50 years. And he was talking about how they're just absolutely embracing it because you just can't get enough radiologists, and how the AI and the radiology are going to go so well together, and already have been, in fact. And he said, we have been using this to an extent for years, but we see huge gains. Advances in autonomous vehicles, and I don't know how many of you have seen the Google Waymo cars that are in San Francisco. They're just absolutely amazing how advanced they are already. If you are going up that way, pre-register a week before because you need to get on the wait list to be able to use them, so you need to register in advance. Some of the darker sides or disadvantages, I guess, obviously job displacement, ethical concerns and bias and privacy, and I'll touch on that in a moment with some examples. Security risks from hacking, and you only have to watch the latest Netflix or Tom Cruise flick to see that there's some AI being taken over, whether it be a nuclear submarine or Fast and the Furious with cars flying out of parking buildings, or Model 3 Teslas, so that type of thing. And then obviously lack of human-like creativity and empathy. And I've actually in this presentation generated quite a few images with AI, and you get, and I reckon it's sometimes a little bit like when you cook something in the slow cooker. It kind of always has a little bit of the same flavour, even though you've made it completely different. It's got you just know it's come from the slow cooker. It's the closest sort of analogy I could get from it. So the good and the not so good. So at the GTC, there was a drug pharmaceutical CEO that spoke, and he was talking about cycle times for drugs and how typically in America it's about 10 years to take a drug to market. And he was saying that with AI, they believe they're going to get that down to sort of 3.5 years. So, and they think that's only a couple of years away from being able to do that. So a remarkable change in terms of being able to augment the good people they have with the technology. This Google Gemini got off to a little bit of a rough start last year. Some of you may have seen that there was a few questions around its bias, and there's a really good Fox News YouTube video with Jesse, the reporter from Fox News, and he's talking about the guy that was responsible at Google for how Gemini behaves and its bias and things, and how his views were heavily coming through, including this image generation stuff. And it's a very funny YouTube video, but that's George Washington there. So, and the headline of the YouTube was, and the news article was, Gemini rewrites history. So it's quite a good one to watch. So if we drill down into the world of compute, this is a bit of a busy slide, but it's from Altman Solon, who is one of the biggest technology analysts in the world, with some big brain people. And it pretty much shows where in the world at the moment where does traditional compute sit? So if you start at the top, you've got the likes of end user compute that might be on-premise in a data center of a bank, or might be in a co-location facility where people are buying tin and putting it into that. And about 15% of the traditional workload sits in that space. A whopping 25% sits in that social media sort of B2C type space at the moment. And then your software as a service stuff around 5%. And then these new market entrances here, like the OpenAIs, and sitting under that, you've also got a GPU as a service market that's where you basically, well, as you said, you're getting GPUs as a service, and then you do what you want with them. And then the big hyperscalers sitting down the bottom. And you can see that it basically is projecting the rise in the generative AI workload of the likes of obviously OpenAI and some of these specialist GPU as a service providers. I think it's slightly undercooked in the hyperscale space and in the consumer SaaS space, because if you look at Meta, for example, they're just consuming massive amounts of GPUs, as are the three big global players down the bottom. So I think that 40% prediction here is probably light. I think the Meta kind of line there is probably light as well, but there'd be some movements in and around that. But that's the kind of prediction. So I said to the Copilot and asked it to draw some pictures for me about large language models and around these words training and inference that most of you would have heard about. Training, which is where you essentially take the computers and feed them lots of information, almost like taking them to university and learning. And it produced this little image of the little computers going to school with the backpacks on. And then when the computers go to work and we're accessing those large language models and that inferencing is occurring, then the computers are essentially in the workforce, and it drew this image of the computers at work and getting out there. So that's sort of that's like the how I would explain to my 14-year-old daughter the differences between the training and the inference side of things. So looking at what sits behind AI and now dropping down into to the chip layer, if you like, you've obviously, and many people here have probably studied computer science, and I've forgotten more than I learned, I would suggest, after 35 years, but the basics of a CPU has been I guess the foundation of more classic compute, and names like Intel have been famous in this space and will continue to be, and CPUs are not going away anytime soon. But Jensen, the CEO of NVIDIA, calls that classic compute, and then he calls the other side accelerated compute. And the key difference and the origins, obviously, of GPUs is graphics processing, video cards, and that's what NVIDIA was famous for. And in that situation, you're having to do lots of things in parallel. Whereas with classic compute, CPU-based compute, it's one thing at a time, and you really have to throw more memory or clock speed and things like that in order to get the performance improvements. So this accelerated world really allows us to break away from that kind of Moore's law type basics and move into this next level. The chips are getting more and more powerful. So this little graph here shows here the wattage of the processor, if you like, so how much power is it consuming and obviously dissipating as heat. And GPUs have been around for a number of years, and the first of the mainstream that we saw coming into our data centers were these V100, first sort of wave of mass-produced data center grade chips. And they were, if you put them into servers and fill up a rack, you're talking about 18 kilowatts in a rack. Then came along the Generation 2 A100s that we've got a lot of in our data centers as well. And then more recently, what's been rolling out a lot has been the H100. And then obviously there is the new chips coming, the B series chips, the Blackwell chips, and they have core wattages of around that sort of 1200 watts, and they'll go even beyond that. And if you pack them into a rack, then you get about 120 kilowatts. So some of that densification is coming in terms of how much you can get into a rack from changes in the processor, but a lot of it's actually coming from how we're cooling them. And we're having to fundamentally change the way that we're looking at cooling. So the latest generation of chips, and this has been around in supercomputing for many, many years. We're basically we're getting rid of those air-cooled heat sinks on the processors. We're connecting things called cold plates. And you've seen this in supercomputing and gaming and things for a while. And essentially what you're doing is putting that cold plate directly onto that chip. It's getting rid of that massive air-cooled heat sink, and you're basically running a glycol mix or similar through those chips. These chips, this is the B200 chipset that was launched last year at the conference, and this is an amazing piece of kit. And they had a mock-up on the stand. I think it's close to shipping soon. Actually, amazing. 72 Blackwell processors and 36 Grace Hopper CPUs, 120 kilowatts a rack, with an amazing NVLink networking backplane that you can see in that picture there. And at Jensen's keynote, he pointed out that you could pass the entire internet basically through that NVLink backplane, that the throughput of it is so amazing. So what does this all mean? And this is the IT side of it. It means it's quite a step change for the data center industry. So I've been in and around this for a pretty long time, and back in the day, it was actually quite easily, because you were talking about racks at sort of 4 kilowatts a rack, like we see in the first picture there. And then over time, we've seen that rise, and we've seen the sort of 25 to 44 kilowatt racks come in over the last few years. But this going beyond this 44 becomes a complete change in how we need to do things. So at the bottom end of density here, cracks and raised floors and things were fine for those 4 kilowatt racks. We've been playing in this space for years with in-row cooling and pods and fan walls and things, covering with air up to around that 44 kilowatts a rack. But moving beyond that 44 kilowatts a rack, we need to be considering something different, and that's moving to the concept of heat exchangers and the like to be able to do that. And no longer is it sufficient just to bring in vast amounts of air from outside. We've hit the limits of air. At the bottom end, we've been able to use chilled water or air for a long time. Really, we need to move to this chilled water based systems in order to be able to do that. So I fed the Copilot again with a little bit of information around what the architecture of a AI-capable data center might look like, and I gave it a little block diagram. And it did a pretty amazing job of actually summarising all of the key components and how they interact in the system. And then I said, can you produce me an infographic, which it did on the right there. And suffice to say, I think our engineering team are going to be around for a while yet, because it's very artistic and pretty, but it actually doesn't really make too much sense at all. So, but it looked pretty cool. So, in terms of what does it mean for data centers globally, it's a pretty big problem. So this is actually 2-generation-old GPUs installed in a traditional data center with a raised floor, and you can see the heaps of space blanked out, massive grills in the floor already, containment, and that's only doing 18 kilowatts a rack, not 120 or beyond. So it pretty much means there's an extinction level event heading for a lot of data centers globally. And I asked for an extinction level event and it drew me up some dinosaurs being taken out, surprise, surprise. But really it's the power, cooling and weight that is becoming a big problem and literally creating dinosaurs out of data centers. And this, when I said, can you draw me a data center dinosaur in the wild, and it came up with this image of an old school data center that was failing, and they're trying to fix it with fans and things unsuccessfully. Breaking that down, what does it mean? If you look at an average New Zealand data center, they've been designed to 2 to 5 kilowatts a rack. They've been designed for weights of in the vicinity of 500 to maybe 1,000 kilos, 2 to 5 kilowatts of power. Raised floors have been used, and some data centers do have chilled water heat rejection, but a lot don't. So a modern AI-capable data center, we're talking 100 plus kilowatts a rack, 2-ton racks, 100 plus kilowatts in terms of power, no raised floor because we need to be, the racks are way too heavy to be able to do anything with a raised floor, and you must have this chilled water heat rejection. And we've been on this journey for a long time. So all the way back in 2007, we made a decision to use chilled water as our heat rejection methodology. And all of our buildings have this as their lifeblood pumping through the data center. So we've been doing essentially almost liquid-based cooling all the way back then. We've got 3,000 in-row cooling units installed across Australia and New Zealand. And we've just been adding on and plugging into this fungible chilled water backplane for many, many years, right through to this next generation. Here's a few projects of our sites all the way back in 2013, 35 kilowatts a rack with in-row cooling, 50 kilowatts a rack in 2019, and more recently, we've been doing deployments in Australia for supercomputing in this space here. Bit of good news, I'm pleased to say all of our operational data centers have now been certified by NVIDIA, so this is a very exhaustive process where we work with their team in San Jose. We have to go through every intricate detail to understand. NVIDIA want deployments to be successful, so they want their technology to be able to be deployed, and so there's an exhaustive process of reviewing the power, cooling, weight and resilience. And we've got them certified in Australia and New Zealand, and at this stage, the only data centre operator in New Zealand to have them certified. So in terms of a summary, AI is here, it's evolving fast. In our personal and business lives, we need to understand it, or we may face an extinction level event ourselves. We're here to support your AI journey. Our data centres are both fungible for the future and efficient. There you go.
Thank you, Andrew. There's time for one question. I have a question, actually, Andrew. So when you're talking about 120 kilowatt per rack, you're just talking electrical or power, or are you talking
power
actually
and the heat out?
And the heat, okay.
Yep.
Okay, so it's not quite as bad as I thought.
No, it's bad.
But it is bad.
Yeah. No, that much power's going in and that much heat's coming out.
Yeah.
Yeah.
Okay, Wolfgang.
Thanks, great talk. So I think it was a couple of weeks ago when this whole DeepSeek thing ripped through the world, created quite a stir. And so I was wondering what your take is on that. So I think it does seem quite likely that people will either with DeepSeek or others will come and build much more efficient AI models. So would you expect that AI data center needs will still grow and just be replaced by more models that are more efficient?
I think what will happen is that if we make it cheaper and more accessible and things, we'll just find more and more ways to use it. And it's just that basic theory of economics, I forget it. It's a long time ago since I studied it, but we'll just consume more and more. I mean, if you look at where AI is at, like where it's absolutely in its infancy. So I think we need that because it will help, right? So I also think that there's some very questionable numbers flying around about really what it did cost to develop and the like as well. So, you know, missing out the couple of $1 billion of R&D spend and just choosing to focus on, you know, that kind of thing. Yeah.
Thanks, Andrew, and let's thank you again.
No worries, thank you.